All right, our final speaker for this morning's session is Brendan Sporer. He works at the University of Michigan, and his field is physics and pulsed power. He's an LRGF fellow, and his residencies were both performed at Sandia National Laboratories, New Mexico. Please take it away.
Thank you. Okay, so this last talk before lunch will be about fusion, MagLIF, and specifically an alternative embodiment of MagLIF on the Z machine using field reverse configurations, which I'll explain. First, many people to thank, starting with my advisor, Ryan McBride, for encouraging me to pursue this sort of exotic topic. Everyone at Sandia for supporting my application and my residencies. Tom at Los Alamos, the local FRC expert in the labs, Aiden, and of course Krell and Chris Moran for dealing with all the logistical issues. I was actually supposed to give this talk last year, and then my flight got canceled on the tarmac, so that was fun. So I'll spend the first good chunk of this talk just sort of motivating the work that I did in my dissertation. So I'll define magneto-inertial fusion on what I like to call the Lawson spectrum. I'll talk about the Z machine, which is a very large pulse power machine at Sandia. I'll talk about MagLIF, which is a fusion program pursued on that machine, and then field reverse configurations for MagLIF. And then I'll get into my dissertation, which was to advance this concept in sort of twofold, an experimental program on our machine at Michigan, and then simulations in an MHD code, which came out of Sandia. So this slide's a little bit maybe an oversimplification, but I like it because I think it helps define magneto-inertial fusion, also known as magnetized target fusion. So it turns out if you just take high temperatures as a given, you can put a pretty simple criterion on getting fusion gain from a plasma, which is just the product of the density and the confinement time. But what's cool is that we're actively trying to satisfy that criterion over something like 10 orders of magnitude. So on the left side, you've got magnetic confinement with very low densities and very long confinement times, and on the right side, you've got inertial confinement with very high densities and very short confinement times. But then you've got this middle ground as well, where you basically try to take the best of both worlds. So you include a magnetic field for thermal insulation, but you do some sort of compression or implosion to reach higher energy densities. So there has been some government investment in this field, most specifically the Linus program at NRL, and then this century the ARPI Alpha program, which funded some of these fusion companies that you may have heard of, which would claim to lie in this area. And it also provided some funding for MagLIF. And sort of the inspiration for this, this blue curve here can be represents the argument made in these papers, originally by the Soviets and then by us, that if the cost of your driver to satisfy this criterion is proportional to the energy it delivers to the plasma and the power it delivers to the plasma, you can actually get a minimum that lies somewhere in the magneto-inertial fusion range in terms of cost of the driver to achieve break-even. So the rest of this talk I'll spend in this sort of on the higher energy density region of magnetized target fusion, which includes MagLIF, and this talk, which will be slightly lower energy density than MagLIF. So I think plenty of people have talked about the Z machine, world's most powerful pulse power machine at Sandia, stores something like 28 megajoules in banks of capacitors around the outside, discharges it through a series of pulse forming sections, to deliver the world's most intense electrical pulse to something that's on the order of a centimeter sized at the center of the chamber. We can do fusion with that in many different ways. One is to just simply pinch deuterium gas puff, which is kind of similar to a dense plasma focus that we saw the other day. Another way, NIF is sort of the king of indirect drive, but we also do indirect drive on the Z machine, where you produce the X-rays with the Z pinch of a high Z wire array instead of lasers in a Hall RAM. And then the last, more recent addition to how we can do fusion on Z is MagLIF, which I'll talk about next. So these are sort of the canonical stages of MagLIF. The idea is that you have your small liner or cylindrical tube filled with gas. It's magnetized by a large set of external coils. You then preheat that gas to several hundred EV using the Z beamlet laser, which is a kilojoule class laser they have at Sandia. And then finally, you fire the Z machine, and you Z pinch that liner and adiabatically compress the fuel inside to fusion conditions. So this has been pretty well characterized by the brilliant scientists at Sandia, and it's looking like the maximum yield on the Z machine is going to be somewhere around 100 kilojoules, assuming we have some upgrades in these stages, the magnetization and the preheat. But on a next class, on a Z-next machine, 70 megaamp class facility, it's thought that this could reach ignition and gigajoule class yield. But what ultimately limits this, this concept is that you have open field lines. So MagLIF is kind of in this very interesting regime where you've got magnetic insulation radially, but inertial confinement axially. And so if you just consider the speed of a deuterium atom, you can see that you have something like tens of nanoseconds to implode the cylinder, and that's why you need the Z machine that's so fast. If you want some sort of axial confinement so that you can go slower, perhaps with a more efficient driver, or perhaps the Z machine in a more efficient mode, you have to have some sort of axial confinement, and so you can do that with something called a field reverse configuration. And so this has been a popular target from the earliest magneto-inertial fusion efforts. The idea is you have a toroidal or azimuthal plasma current, but no, and so this is a compact toroid sort of in the same family as spheromax and tokamaks and that sort of thing, but there's no toroidal field, so there's no helicity, and you're not subject to the same beta limits as those other toroids, and you can actually achieve beta near 1, which is good because you don't want to waste all your compression energy on magnetic field. You want to be compressing plasma. They're robust and translatable, so once you form them, you can actually, by putting a slight gradient in the field, you can kind of squeeze them out the end of the tube. So that allows you to form them in one place and then shoot them down the field to another place to be compressed or something. And finally, as you compress them radially, they'll actually tend to compress themselves axially due to magnetic tension effects in a sort of a bid to maintain the aspect ratio. So you can actually get better than R² compression, volumetric compression, from a cylindrical implosion. They're usually formed by the reverse theta pinch method over here, which I'll go through because that's how we're going to form them as well. So it looks very similar to MagLIF, where you have this tube filled with gas and axially magnetized. Then you pre-ionize the gas, just pre-ionize. You don't have to preheat like in MagLIF, so it just needs to be conductive, so something like half an EV, which very much simplifies the process. And then you quickly reverse the applied axial field. And what happens is the plasma wants to hold on to its forward field, so you'll get these reconnection events, ideally at the ends of the tube, and then you'll go through some sort of contraction phase to reach the sort of pseudo FRC equilibrium. And you get this reconnection and contraction actually adds some natural preheating up to the 100 ZV that you need to do the adiabatic compression. And because of the reconnection that's involved in this formation method, this can also be an alternative platform to study reconnection physics. So Steve's idea, which I won't claim as my own idea, was to use that you could do a field reverse theta pinch with a fairly simple modification to the MagLIF hardware. So the idea is that you use the MagLIF bias coils in a standard way to produce an axial field in one direction, and then you use something called an automag liner, which is also something under development at Sandia. And what that is you have helical cuts in your liner and then you fill them with dielectric or something so that you can hold the gas inside. But the foot of the Z pulse will actually travel helically and therefore produce an axial field inside the liner. That reverses your field, and then as the Z machine ramps up, you just flash over everything and everything compresses like a Z pinch, and you compress the FRC in situ inside the liner where you just created it. So that's a very interesting idea, and what's even more interesting is that in this publication by Steve and Matt over there, they showed that Steve did a fairly simplified Lasnik simulation where he formed an FRC and compressed it using an assigned 500 kilojoules of liner energy and was able to get Q greater than 1, which is pretty interesting. Here's some screenshots of that Lasnik simulation. So that brings me to my dissertation work, which was the idea was to advance sort of the readiness of this concept. So I did that in two arms. One was experimental using the Maze linear transformer driver, which is a megaamp class fast pulse power machine at University of Michigan. And the idea there was to just demonstrate that first step, the field reverse theta pinch, where you just form the FRC, and then you need the full current of Z to compress it. And then the second arm was theory and computation. So this was using a code called Kraken, which is under development at Sandia by Chris Jennings, came out of the Gorgon MHD code. And the idea here was to initialize the FRCs that we're hoping to form and then allow them to decay. They will decay because they have a plasma current, so they'll resistively decay over some time scale. So here's the platform that I eventually developed on Maze. It doesn't look too much like an automag experiment or a MagLIF experiment, and that's because I wanted it to be repeatable, reusable, so I could get multiple shots without shattering the quartz tube that I'm using to contain the gas at the center. So I'll just go through sort of the stages here. So first you apply this low bias field using this external set of bias coils, which is pulsed. You then pre-ionize the gas, which I did using a method called Z-discharge pre-ionization, which I won't go into, but I like to think of it sort of like a neon sign tube where you've got electrodes at the top and bottom of this glass tube and you're just doing a discharge through the tube. So that pre-ionizes the gas, and then the last stage is field reversal, so then we fire Maze. That passes several hundred kiloamps of current through this helical load hardware here, and that reverses the field to produce this FRC inside. And then step 4 is take pictures with my favorite diagnostic, which is a very nice fast framing camera that we have at Michigan. And so those pictures that I'll be showing you in the next slide are looking through this top window, so top down on this FRC that would look like a ring of plasma. So here are those images. Each row represents a sequence of images for a shot, and these are different conditions, initial conditions of the bias field and the pre-ionization. So the top row shows 0 bias field, and so this is basically a theta pinch, where you're just a fast rising axial field. No pre-ionization, so you see it's a fairly slow implosion that stagnates on axis. If you add in a little pre-ionization, the pre-ionization actually adds a lot of non-uniformities to the gas initially, so that will seed some instabilities. So you can see some very high mode sort of fluting instabilities coming out there. Then when you add in the bias field, but no pre-ionization, you still get what looks like a theta pinch where something sort of comes in and stagnates on axis. However, when you start adding in pre-ionization, and so in this case what's basically happening is the gas is not conductive enough, so it's not holding on to its forward field. So you essentially are just doing a theta pinch because the field is getting pulled out before you compress it. But when you start adding in pre-ionization, then you can trap the bias field, and what happens is as you get better and better pre-ionization, you see these sort of smoke-like rings be created and persist for quite a long time. So I also did some measurements, some magnetic measurements, using what we call excluded flux B dots or B dots, and these are basically these tiny little flux loops that are made out of this very small coaxial cable, and you place them on the outside of the quartz tube, so it's a non-perturbative measurement. And what you're trying to measure there is the effect of the FRC in the center of the tube essentially bulging out the axial field that you're applying. And so that field gets excluded and bulged up against the coil or the flux conserver, and you can measure that, and that's proportional to the excluded flux radius, or essentially the radius of the plasma. So here's some of the results of that measurement. So this 2D plot is versus axial position, and coming forward is in time. And what I'm plotting is the height is essentially the excluded flux radius, a normalized excluded flux radius. Here is the Maze current pulse coming up to peak current. And so what you see in the case of an FRC shot is a significant amount of diamagnetism associated with this ring, and actually the radius here matches pretty well to the radius of this ring. Whereas with a theta pinch, you see a significantly less amount of diamagnetism. Here's some interesting instabilities. So as I mentioned, theta pinches are subject to generally very high mode fluting, so you can see this sort of spiky appearance here. Whereas FRCs are more subject to low mode instabilities that we call rotational and wobble instabilities. So here's some examples of those. This one's interesting because it's sort of like an n=3, which is less common. So moving on to the computational part of my dissertation work. So the idea here was to initialize FRCs and allow them to decay and try and use existing anomalous theory to see if they match the existing theory. So first, to initialize an FRC, you want to use a pretty good equilibrium to start with, because otherwise if you're too far off in the first couple time steps, everything will sort of snap and you'll introduce too much violence and everything will just break apart. So to get a good equilibrium, I used the equations from this paper, which are complicated, but ultimately just a function of some simple FRC parameters like the external field, the temperature, the elongation, and the radius. And it also includes this sigma parameter, which is nice, because that controls how the field behaves at the ends of the tube. And so this And so this case, where it sort of flares out above the FRC, is more like an automag that has a finite length with the FRC inside of it. So here's an example of decay. I think this one was actually maybe classical, but you can see in this case, this is a fairly cold FRC, so decays in about 1 microsecond. You can see differences between the case with flare and no flare. The next step was to implement an anomalous resistivity treatment. So it's well known that in order to properly model the decay of FRCs, you need to treat them with anomalous resistivity that basically is a result of micro-instabilities from the plasma current. And so I found that using the Codura treatment, which I don't have a reference for actually, I'm realizing, sorry about that, but using this treatment with fitting factors of just 1 actually give a very good fit to the empirical LSX equations. And so Steve's FRC, which is very hot, actually has a very long lifetime. So you can see that matched well with the Codura treatment. And so this empirical equation came from an experiment called LSX, which was a very large and well-characterized FRC experiment in the 90s, and they came up with these empirical equations. Another thing I was happy with how it came out was an ejection estimate. So as I mentioned, if you have a slight gradient in the axial field, you can sort of move the FRC and shoot it out the end. And so I was trying to figure out if your automag liner is not perfect and you have a gradient in the field, how long will you shoot the FRC out before you can compress it? And it turns out that's pretty forgiving, even for significant burn temperatures. Unless you're burning for many tens of nanoseconds, you can tolerate a pretty high gradient in the field. And the simulations matched very well with this simple estimate that just came out of, that's only dependent on the temperature and the length scale. The last thing I did was some synthetic imaging. So this was using the SPK package. So thanks to Aidan Crilly for getting me set up with that. And actually, when you do the synthetic image, so this is visible synthetic image to match the visible fast framing images that I was taking in the experiment. And so you can see that for these initial simulations that I did where I was just initializing, the profile does not look very hollow, as we would expect from the experiments that were showing these sort of ring-like structures. And it turns out to recover that ring-like structure, you actually need to do the formation. And a lot of times when you would, so I implemented a thing that would change the flux function at the boundary basically to emulate a field reverse theta pinch. And that tended to produce these very small FRCs that were moving very fast. But it also recovered this hollow emission profile, which I think matches the experiments pretty well. So in conclusion, I think that compressing FRCs in a MagLIF platform could represent an exciting new path to fusion gain on the existing Z machine. Experiments on the Maze driver have demonstrated high-density field reverse theta pinches pre-ionization and have likely produced these long-lived closed-field plasma targets that are ripe for more study and better diagnostics. Simulations in Kraken are suggesting that the existing theory is applicable to the HED regime, and the FRC lifetime should be suitable for the compression, and continued pursuit of this concept in simulation and Mykonos experiments is encouraged. So thank you.